Hi, this is a first physics lecture here on the first topic of measurement. Okay, this is the first chapter, the first topic. It is actually quite simple and basic, but important. Okay, because in every A-level exams, the first question of the paper will be on this one. So you have to be able to score for all questions, especially the easy marks. If you score in the easy marks, okay, that's fine. If you do not score it for the easy marks, you'll find that your ranking goes down a lot. Okay, I mentioned before the A level is all about ranking exercise, so that's important. So please take this chapter seriously as well. Now, at the start of the chapter for the lecture notes, we'll put down this thing called the learning outcomes. This is actually the syllabus. Okay, so what's in the syllabus, what you're required to know, this is it. So we put this at the start so that at the end of every chapter, once you have finished, go back to the syllabus and use this as a checklist. Okay, use this as a checklist. And if you can understand this and you can apply this, internalize it, and demonstrate this, then you're done. Then you're able to do this. And that is what studying is all about. All of you will study hard, but it's important to also study smart. Okay, so let's look at the first point of the syllabus. Recall the following base quantities and your SI units. There are actually seven base quantities, but only six are in the syllabus: the mass, the length, the time, the current, temperature, and amount of substance. So these are the six base quantity that you need to know. And if you can, say it out to your friend or you can write it out on your own, that shows that you have already demonstrated that you understand this point. So this is accomplished. So this is how you should study. After you finish the syllabus, do the tutorial and then come back. If you can demonstrate all the points in this syllabus, use this as a checklist, then you have fully understood. And that's good enough, then move on. When you study your physics, do not just think of, oh, I've to spend so much time and things like that. No, study objectively, study with a purpose. Once you have fully understood, move on. Okay, so that's that. So let's begin. So the first thing is about SI unit. Now, I'm sure you've heard of SI unit before in secondary school, but what exactly is SI? So SI units is basically this one. This is a French word which I cannot pronounce as well. So maybe I'll get someone to pronounce it for me.
Système international d'unité.
Actually, I didn't really get that. So maybe let's hear it one more time.
Système international d'unité.
I still don't get it. Okay, so for the A level, just take it as SI unit is good enough. Now, quantity is something that can be measured. So, of course, you should know that in physics, in science, measurement is very important. You measure and you acquire data and you form conclusion based on the data. So each measurement should have both the magnitude and the unit. So the magnitude and unit together, then it makes sense. Okay, like for example, Usain Bolt set the world record in a 100-meter sprint at the time of 9.58 seconds. Okay, so if you just say 9.58 without knowing what unit, that is not totally helpful. Okay, so the unit is important as well. Like for example, Joseph Schooling, we know he's a reigning 100 fly Olympic gold medalist, and he won it with a time of 50.39 seconds. Okay, 50.39 seconds. But if you look at the American record books, Joseph Schooling 100 fly record is not that. It's 44.51 seconds. So how did he do it? Well, because basically in the US, especially in terms of their school races, it's not 100 meters, it's always 100 yard. Their pool is of a different length. Okay, so Joseph Schooling's record in the US for 100 fly is 44.51 seconds, but that's because it's 100 yard. So it's a different comparison. So you need to know that for a quantity, the magnitude and the unit together, then it makes sense. Okay, now let's go back to it. So now let's talk about the base quantities and their units. So as earlier mentioned, this base quantity, there are seven base units. Okay, These are the 7, but as listed in the syllabus, because you are often saying that, oh, is this in the syllabus? Is that in the syllabus? So if you look at the syllabus, it says that only these 6 are in the syllabus. Okay, the last one, luminous intensity, where its measurement is of a base units of candela that is not in the A-level syllabus. You don't need to know. So you absolutely need to know these 6. Length is meter, mass is kilogram, time is second, amount of substance is mole, temperature is Kelvin, current is ampere. Okay, so that's that. So these are the SI base quantity and SI base units. Okay, so let's move on. So things that simple, we just move on. Don't have to waste time. Keep on looking at it and memorizing things like that. So the thing is to understand. So the next thing that's important is derived unit, okay, and quantities, or rather derived quantity and unit. Now, a derived unit can be expressed in terms of products or quotient of a base unit. Okay, for example, what is the units of area? We know that it is square meters. Please don't say meter square. Okay, it is square meter. How did we get square meter? Well, because area is a product of its length and the width, which is also a form of length. So that multiply together, you have square meter. So this square meter is a derived unit. Don't ever say square meter is a base unit, because the base unit is meter, but the derived unit is square meter. Okay, so I think these are all basics that you know, so you can just read on yourself, which I do not need to read it out to you. Okay, so that's that. Momentum is the product of mass and velocity. So how do you get that? The unit of mass is kilogram, the unit of velocity is meters per second. So the derived unit for momentum will be kilogram meters per second. So that's that. Okay, so these are quite straightforward, which you can acquire yourself. Now, so let's go forward. There are other derived unit that are collectively put together. So, like for example, Newton. Okay, Newton is not a base unit. So Newton is a derived unit. Okay, it is the Newton is a unit that is used to represent this kilogram meters per second square. But how do you get that? Okay, so if you need to know the derived unit in terms of base units, this is the first thing that you ask in exams, or I mean, this is one of those things that they can ask in exam. They give you the derived unit, but they ask you what is the unit in terms of base unit. So this is how you do it. Okay, if I write on it, the words will jump, so maybe I don't write it. So let's talk about pressure. Well, it's all about pressure, right? Okay, so the unit of pressure is Pascal. But if I want Pascal to be written in terms of base unit, which means that the unit should only have things that is part of those 6, okay, here, which means that the unit should only have meters, kilogram, second, mole, Kelvin, and ampere. So how do I do it? Well, we know that pressure is equals to force over area. Okay, so pressure equals to force over area. So the unit of force over unit of area will be equals to, what's the unit of force? Kilogram meters per second square. What's the unit of area? Equals to square meter. So this together will become kilogram per meter per second square. Okay, so that becomes the derived unit of, that becomes a unit of pressure in terms of the base unit. So this is how you work it out. The examples for the rest are all here, so do try out yourself. Okay, so you know the unit, you know the derived unit for energy is joule, but if I want the unit of energy in terms of base unit, what do you do? Well, you do this, take the force multiply by distance, because you know that the work done is joule. And how do you get work done? Force multiplied by distance. Correct. So if you take the base unit of force, which is kilogram meters per second square, multiplied by the unit of distance, which is meters. You put them together, you will get this. Let me see. Yeah, it wouldn't jump. Oh, it still jumps. So that is the answer, kilogram meter square per second square. Okay, so please try this out. Try this out. Put the paper, cover it, work it out, and then you compare. So remember, to study, you have to have a pen. You have to annotate. You have to be writing on your notes, like what yours truly is doing. Because in the exam, you score marks based on what you write, not what you read. Reading is low level. It does not help. I mean, it does not massage or train or exercise your mind at all. So the study is to write. Okay. So let's go back to this one. Work example one. Express the Newton in terms of SI base unit. Well, we mentioned just now. So the final answer is kilogram meters per second square. Okay, so this is it. But this work example, now every single work example has a purpose. We do not just randomly choose questions and just write it out to fill the page. We don't. Every work example, there is a purpose, and the message for work example one is this. Now, I'm sure almost all of you will be able to get this answer. That is not a problem. But to score the marks, as far as Cambridge is concerned, they are concerned about presentation. Okay, they are concerned about presentation. So do not provide a presentation such as this. Okay, this is a common error. Now let's look. They want you to express Newton in terms of SI unit, SI base unit. Now, Newton is a unit. Okay, Newton is not a quantity. So had you presented your answer in that form, Newton equals to mass times acceleration, therefore equals to kilogram times meters per second square, you will lose marks. You will be marked wrong. This will be penalized because Newton is the unit of force. Newton is not force. Okay, so presentation is important as well, unless it is a calculation question. Okay, unless it is a calculation question, if that is so, all they want is to see that your final calculated number and quantity, units, magnitude is correct. Okay, unless it is a calculation question, but this is not. This is a show question. This is an express question. Express means show. So they want to see the presentation, and marks will be given to the presentation. So please be very aware of that. Okay, so work example two. Now, the drag force. What is drag force? You learn in chapter 4. Drag force is produced, the formula for the drag force is this: force multiplied by A, which is a constant, multiplied by R, which is a form of length, multiplied by the velocity. Okay, now at this point, you do not know, but don't worry. So if you do not know, they give you the equation, you can still solve this. What is a suitable unit for A? So what is the suitable unit of A? So what you do, make A the subject of the formula. Okay, so A equals to F over RV, and then present it correctly. The way to present is to use it the bracket. The bracket, okay, sorry, I did not mention this, emphasize. The bracket is a form to denote unit of. Okay, so you can that will be a shortcut. So you define this. Let the square bracket denote unit of, and from then on, in the rest of the presentation, you'll be recognized that anything inside is unit of. So unit of A equals to Newton over uh, Newton over meter and meter per second. Okay, because we are talking about unit of. So N is a unit, meter is a unit, meter per second is a unit. And therefore, the final answer is this: Newton per meter square second. Okay, look back at the question. They say, what is a suitable SI unit? They did not mention the word base unit. Okay, but if the word base unit had been there, okay, if they say what is a suitable SI base unit, then this answer would not have been acceptable because Newton is a derived unit. So the possible answer would be this: instead of Newton, you put kilogram meters per second square, and the whole thing becomes that. Okay, so there are two possible answers here because the question did not insist on the word base. But if the answer had insisted on the word base, then only the second answer is acceptable. So that is the purpose of work example 2. So each work example is to communicate something to you. Okay, so this work example is to tell you to look out for, did they use the word base? If they did not use the word base, well, the Newton, which is a derived unit, is fine. Okay, so these are all very simple. Once you understand it, that's it. Please do not go back to these simple things and read and read and read over again. Don't. Okay, for this chapter, the earlier part is simple. Whatever I go through in this first lecture video is simple. The slightly more difficult one is at the later part. Okay, so next thing we're talking about the concept of homogeneity. Okay, which means that whether is the equation homogeneous. The equation being homogeneous means that it is dimensionally consistent. Dimensionally consistent means the unit have to be correct. Okay, like for example, if you look at this equation, b equals to u plus at. Okay, you know this equation from your secondary school day under the second chapter of kinematics. B equals to u plus at. So, I mean, you've learned this before. Of course, this equation has to be correct. Okay, but I mean, let's test it. So, it is correct if it, it is correct. If it's correct, it has to be dimensionally consistent. What's the meaning of dimensionally consistent? It means that every single term have to have the same unit. So the unit of V is meters per second. The unit of U is meters per second. The unit of AT, A is acceleration. So acceleration is meters per second square. The unit for time is seconds. So this combined together give you meters per second. So there you have it. They are all the same, so they are dimensionally consistent. So that's all there is to it. Okay, so I'm sure this one you understand. I do not have to go through in more detail. Now, just take note that correct and homogeneous are two different things. Okay, so if all the units are the same, we can conclude that it is homogeneous. But whether it's correct, well, it's a different story. Like for example, look at this equation, this one here. Okay, V equals to 5u plus at. Now, if we look at the unit of V, meters per second, look at unit of 5u, meters per second. Look at the unit of at, meters per second. So they are homogeneous. But is it correct? No, it's not. With this 5, it makes the equation wrong. So this is an incorrect equation, but it is homogeneous. Okay, so take note of that. So let's look at the equation here. The motion under an object constant can be described by this equation: v squared equals to u squared plus 2as, which I think we've learned this in O level as well. So find the unit of s. So that's should be easy, right? Because the unit for v squared is meter square. Meter square per second square. Unit of u square is meter square per second square. So everything, so this one should also be meter square per second square. Okay, so that's it. So 2as, so unit of as equals to meter square per second square. Okay, they want the unit of s, so the unit of s will be equals to meter square per second square divided by the unit of acceleration, which is meter per second square. So this divided by that give you meter. So the unit of s, which is displacement, is equals to meter. Okay, so this is just a simple demonstration. So there's something interesting in this. So sometimes you put in some of these interesting historical occurrences that hopefully will spice up the subject a bit. So do look at all this, scan this QR code, or go to this link, and then you'll see the tragic episode. But of course, in this case, this, I think, I can't remember what's the exact name of it. It's in the link. Okay, this device actually burned up in the atmosphere because of wrong calculation. Why wrong calculation? Is because you know that the British, let me see if metric. So because they did not convert the unit in the calculation. Okay, so you know one group uses kilograms, the other group uses pounds. Okay, one group use meters, the other group use yards. Okay, so because they did not convert the unit correctly, so the calculation was wrong. So the rocket science formula didn't work, and then the wrong calculation caused this thing to burn up in the atmosphere. Okay, but at least there were no human tragedy there, because there were no casualty there, because this was an unmanned object. So this actually took place in 1999. Okay, so do read about that. Now, next, work example 4. Okay, so this one I don't have to go through, is self-explanatory, except for what this work example try to tell you. They say determine if the equation is a correct one. Okay, so what you do is that you look at two aspects. First of all, is it homogeneous? Okay, now if you test it out, yes, it is homogeneous. This is the Bernoulli's equation, which is unfortunately no longer in the syllabus. So pressure plus half density velocity square equals to density acceleration due to free fall times height. Okay, so the unit of this and the unit of this and the unit of this are similar, so you can test it here. Okay, they are similar. So the only thing you can conclude is that the equation is homogeneous. Okay, but you cannot comment about the correctness. Okay, so just remember, if they ask you that is it correct, in this case you cannot comment whether it's correct, but you can prove that it is homogeneous. So your conclusion must be the only thing that you can prove. Okay, so in this case you must mention that it is homogeneous, but it cannot be certain if it is correct. Okay, next thing, very simple, but it's important. They like to ask this in the A levels, maybe through the multiple choice. I think it appeared in the multiple choice uh, question for the last year's A level exam. So you need to know this. Okay, P is pico, N is nano. The next one is mu is micro, M is milli, C is centi, D is deci, K is kilo, big M is mega, big G is giga, big T is tera. And what does it all mean? It all means this. For example, M is milli means 10 to the power of minus 3. Okay, 1 millimeter equals to 1 times 10 to the power of minus 3 meter, or equals to 0.001 meter. Okay, so these are things that you already know, but I think at O level you only learn from milli to kilo. So for A level, let's expand it. Micro, 1 times 10 power minus 6, nano, 1 times 10 power minus 9, and pico, 1 times 10 power minus 12. So you're expected to know this. If you're given a quantity, okay, like for example, the current, okay, the photoelectric current you learn in chapter 18. The photoelectric current is 3 picoampere. So if you see 3 Pa, it means that it is 3 times 10 to the power of minus 12 ampere. Okay, so these are things that you need to know yourself. So that's that. Let's move on. So this is the work example. Which of the following? This is June 05 question, but this kind of question have come up year over year. So I think last year it came out as well. Okay, pico minus 12, giga 9. So the answer is C. Okay, it's really as simple as that. So once again, please do not discount the simple question, because you have to be able to score. In the simple question, it's a ranking exercise. If you cannot score the simple marks, it is more costly. let's move on. Now, oh, this thing is a bit slightly more tricky. Making reasonable estimates. So this is part of the syllabus as well. In the early years of this H2 syllabus when exams were in 2007, 8, 9, 10. Oh, lots of questions on this. So you have to be able to make reasonable estimates. And the key word here is estimate. Okay, it's not measurement, because measure, you use an instrument to measure. Okay, and so this is not a calculation, this is an estimation. So what's the significance of that? Okay, now, as student of physics, we ought to be able to be aware of the magnitude of physical quantity of daily life. So let's look at this work example. Give reasonable estimate. So this is the term that Cambridge use in exams. Reasonable estimate. So the answer can vary, it's not going to be like fixed in some cases. But for the first one, 3 cans of Pepsi or 3 cans of Coca-Cola. You all know that each can is about 325 ml, 330 ml, 340 ml, and things like that. Or maybe in some cases, their smaller can is 225 ml. I think what is served on the aeroplane is 225 ml. So in this case, they mentioned 330 ml, so 3 cans is 1 liter. So how much is 1 liter? It's about 1 kilogram. Okay, but even if it's even if they do not mention this 330 ml, well, how much is a can? A can can go from 225 ml to 330 ml. So what I'm trying to say is that the answer may not be fixed. In this case, because they put 330 ml, so three of them is 990 ml, so it's about 1 kilogram. But the key thing, okay, what they are looking for to give, whether to give you the mark or not, is that your answer has to be one significant figure. That is the thing. Okay, it may not be that accurate, it doesn't matter, but they're looking for one significant figure because it is an estimate. You did not measure. So it can so your answer cannot be that precise. Okay, so if you have put, if let's say this is not there and you put 0.7 kilogram, that is fine. Okay, because it's an estimate. As long as the final answer is one, as long as the final answer is one significant figure. So what's the mass of the medium-sized car? You may not know. Some cars is 800 kilograms. Some cars is 1,200 kilograms. Some cars is 1,500 kilograms. You may not know. Okay, but you give your answer to one uh, significant figure. You put 1,000 kilograms. That's all that they want. Okay, it may not be that accurate compared to the true value, but it doesn't matter. It's an estimate. Give your answer to one significant figure. What is the length of a football field? Well, a correct football, a football field that is used for FIFA tournament, for international matches, it has to be 105 meter by 68 meter. Okay, so this is a standard football field size for a FIFA tournament. Okay, for international matches. But I mean, to get 105 to get 68, you have to measure. But if we ask you to estimate, give it to one significant figure, 100 meter. That's all we're looking about for. Reaction time of a young person is 0.2 seconds. So don't worry if you think it's 0.1 seconds. Don't worry if you think it's 0.3 seconds. Okay, some people may just have slower reaction. So if you put zero point 0.1 seconds, it's acceptable. If you put 0.3 seconds, it's acceptable. 0.2 seconds is fine, because what we are looking for is one significant figure. Okay, so the estimate part is 1SF, the reasonable part is your judgment. If you put the reaction time of a young person is 1 second, 1 second you'll be marked wrong, because while the estimate part is okay, it is not reasonable. 1 second, seriously, if you start the 100-meter race and then they fire the gun and you only start running 1 second later, now that is not reasonable. Okay, so that's what it's about. So now sometimes you have to calculate, your estimate involve calculation. So work example 7, these are all typical Cambridge questions. So this for example 7 is to tell you that, okay, some estimate you need to do some calculation. It's not just intuitive, it's not just you think through the answer. Estimate the average running speed of a typical 17-year-old. So it's about your age, 2.4 kilometer round. So how do you estimate the average speed? So the distance, we know 2.4 kilometer is 2004. The time, so what is a reasonable time? If you say 1 hour, that is not reasonable. Okay, 12, so let's say 12 and a half minutes. So if 12 and a half minutes multiplied by 60 seconds, if I calculate, I'll get 3.2 meters per second, but they want an estimate. Please give your answer to one significant figure. So please keep your answer to 3 meters per second. Then you'll get the full marks. Okay. If you write something, if you leave your answer like that, you'll be marked wrong because that's not estimate. Or worse, if you put 3.23 meters per second, that is clearly not estimate because you cannot estimate to such a high precision. So I hope you understand that. Estimation, one significant figure. So that is what it's trying to tell you here. Okay, so this is a bit more difficult. Okay, because this is the part where they say which estimate is realistic. Realistic. So it's testing you on on you knowing what is reasonable. Okay, so let's look at the first one, the kinetic energy. So this is actually a multiple choice question, 2008 paper 1 question 2. The KE of a bus traveling on an expressway is this. So if you ask yourself, hey, in the expressway, how fast does a bus travel? But it's a bus, so in Singapore is limited to 60 kilometers per hour, but you have to do your calculation in terms of SI unit. So it's meter per second. So the double decker bus is about 10 tons. So if you calculate the KE, it's about 2.02 megajoules. Okay, but 30,000 joules, therefore it is not reasonable. So it is not realistic. So option A is wrong. The power of a domestic light is 300 watt. That is very high. 300 watt is more like those heating thing. Okay, so even a single fluorescent light bulb in the house is just a few watt only. So 300 watt for light, no, it is not reasonable. It's not realistic. Temperature of a hot oven is 300 Kelvin. Now 300 Kelvin is only 27 degrees. 27 degrees is room temperature. You cannot cook anything. So it is unreasonable, unrealistic, wrong. So let's look at this. The volume of air in a car tire is 0.03 meter cube. Well, you just make a rough estimate. So we estimate the dimension of a car tire to be like that. Okay, it's a thickness of 10 cm, it's a width of 20 cm, and this the space there is 40 cm. So with that, you can do the calculation. So volume of air is equals to pi rs square times the width. So if we take the outer volume minus the inner volume, which is what this equation is trying to do, I get something like this, 0.03 meter cube. So it is a reasonable estimate. So D is answer. But okay, now if you look at this dimension, you'll say, how would I know that the thickness of tire is 10 cm? How would I know that the width is 20 cm? I don't even drive. I'm underage. I don't have license. It doesn't matter. If you use different numbers, you probably get a different answer. You will not get 0.03, you get 0.02, you get 0.04, you get 0.05, so be it. But answers like 0.02, 0.04, 0.06 even, this answer, you may get this answer if your all these are different, but they are of the same order of magnitude as that. So that is reasonable. Okay, so that is how you do it. So don't worry that if this is a structured question and your answer is 0.02, 0.04, 0.06, it will still be acceptable. Okay, so that you do not have to worry. Okay, let's move on. Uh, just need to answer text. Okay, so sorry about that. So the following year, they asked this question. give a reasonable estimate of the area of the island of Singapore, giving your answer in an SI unit. So, give an answer in the SI unit, meter square, kilometer square. I think it's easier to give it in terms of square kilometer. Okay, so this is a let me see. This is a paper 2 question 1. Okay, so this is a structured question. Okay, so uh, uh, so to do this, well, we estimate that Singapore is about maybe what, left to right is about 50 kilometer, top to bottom is about 20 kilometer. Okay, so if Singapore is a rectangle, it will be 1000 square kilometer. Okay, because 20 times 50 is 1000, but it's not a square, so we estimate that Singapore is only about 60 to 80% of the rectangle, so the area of the island is about 700 square kilometer. So this is how we get the answer. Okay, and this is the working, so we show the working and we get this answer, 700 square kilometer. Okay, the actual area is 715.8 square kilometers, so that's fine. But once again, can I assure you that if your answer is maybe I mean you may not know this that well, especially if you're not a Singaporean. If your answer is about maybe even up to 500 square kilometer, 900 square kilometer, well, you will still get the mark. Okay, don't think that it has to be as close to the truth as possible, the real value as possible. No, because as long as the order of magnitude is correct, you'll get the marks. Okay, but so if your answer is like 10,000 square kilometer, now that is not reasonable, because this is 7 times 10 to the power of 2. Okay, and this is 1 times 10 to the power of 4. So 10 to the power of 4, 10 to the power of 2 is a huge difference, so that is not a reasonable estimate. So once again, for questions like this is not a multiple choice question, this is a structured question. Even if your answer is 500, 900 is fine, as long as give your answer to one significant figure. If you give your answer to 715.8, you tell yourself, I know, I studied in geography, the answer is 715.8, and you write down 715.8, you will be wrong, because that is not an estimate. Clear? Okay, let's move on. Now, error and uncertainty. Okay, so this is the next part. Now, let me see about the timing. Okay, so this is the next part, error and uncertainty. Now, when you do any measurement, it is not perfect. There's bound to be error and uncertainty. Okay, and the errors and uncertainty can be random or systematic. Now, this is very important. They ask this every other year. You need to know what is a random error. You need to know what is a systematic error. That's very important. Okay, now why is there error? The error can come from human, and actually most of the time is human error. The error can come from the machine, the instrument, the technique, the material, the environment, maybe the temperature, maybe it's very hot, it causes the measurement to be wrong. But just remember, an error is an error. An error is not a measurement. So this question that they ask every other year very often, what is a random error? Or what is a systematic error? Okay, you see that they ask this very often, and your answer must be like this. So in terms of random error, a random error is an error which causes the measurement. So this which causes the measurement must be there. Okay, a random error is an error which causes the measurement to be sometimes larger than the true values and sometimes smaller than the true values. Okay, so in the notes, anything that we box up, okay, anything that we box up are things that have been often asked. So anything that we box up, please be able to, okay, one way is to say memorize, but please be able to write out the sentence on your own. These are those that are often asked. Okay, so what does this mean? If let's say the true value is here represented by this arrow, and your measurement okay, is sometimes here on the right side of the true value, sometimes there on the left side of the true value, then it means that there is random error. Because the random error has caused the measurement to be sometimes larger than the true value here, or sometimes smaller than true value here. Okay, because accurate means here dead on the true value, but it's a bit to the right, a bit to the left, that means there's random error. Okay, so random errors are equally likely to be positive or negative, and they can have different magnitudes. Okay, what has happened? Okay, now, so common mistake. So as listed here, common mistake. Please do not write random error is a measurement that is sometimes remember random an error is not a measurement. So don't write it in this form. Okay. So what are some of the possible causes of random error? If the scale is too far apart, like here, if the scale is too far apart, so what is this? It's not exactly in the middle. It's not near 6, it's not near 5. So how do I read this? Or some fluctuation in temperature because ambient temperature changes. I mean, if the cloud move out of the sides of the sun, then it's cooler, right? So the temperature affects things. Okay. Parallax error, you place your eye at the wrong place, then your reading may be wrong, or inability of experimenter to repeat his action precisely, because when you take measurements in experiment you always take repeat reading, but can you replicate the exact same way in which you measured? So these are some causes of random error. We will make the temperature, you'll make the measurements sometimes larger or sometimes smaller because small fluctuation in temperature. Temperature affects readings, affects measurement, absolutely. But sometimes the temperature can increase, sometimes the temperature can decrease. So it will affect the reading to be either one way or the other. Okay. Now, what is systematic error? Systematic error is an error which causes measurement to be either always larger than the true value. There, this is the true value, is always larger. So there's nothing to the left, it's all to the right, or always smaller than the true value, which is in this case. Okay, so systematic error. So systematic error, some of the causes could be due to zero error of the instrument. If the instrument, like the vernier calipers, if there's a gap in the first place where it doesn't start from zero, it starts from let's say 0.01, then every reading that you get will be overestimated by 0.01. Okay, so normally a systematic error is caused by the instrument poor calibration. Okay, or maybe in terms of calculation use the wrong value, like for example G acceleration due to free fall in secondary school they say is 10, but in A level we need to be 9.81. If you always use 10, then your answer will always be overestimated. Okay, so that is very important. But once again, what is systematic error? This sentence is boxed out. You need to be able to replicate that. But one thing that students every time write wrongly is that they say systematic error is an error which causes measurement to be always larger or smaller than the true value. So don't write it that way. You must say always larger than the true value or always smaller than true value. The word always must appear twice. Think about it. If the word always does not appear twice, if you take out the second always, then it is same as a definition for random error. Okay, so for systematic error, the word always must appear twice. So this is also very important, the distinction between precision and accuracy. Okay, precision refers to the degree of scatter. Accuracy refers to the degree of agreement. That means how accuracy means is it how close is it to the true value. Precision refers to the spread. So please read this. Please read this. It is boxed up. So you need to know this. Read this, but it's easier to demonstrate. So let's look at this. Okay. So these are important now, but in the interest of time, I think sometimes you learn better through example. So example 10. Four students A, B, C, D make a series of measurements for acceleration due to free fall The table shows the results. So which student obtained a set of result that is precise but not accurate? Okay, so let's look. Accurate means we know the value of G is 9.81. So if the average value is 9.1, then it is accurate. Okay, if the average value is not near 9.1, then it's not accurate. So let's look at student B. Okay, let's look at student B. Student B, this for reading, the average value is 9.69. So it is not accurate. Okay, so this is not accurate. Then, so B is not accurate. So to see whether is it accurate or not, you just see whether the average value is it 9.1. So let's look at student A now. Student A, is it accurate? This, if you average out, yes, it's about 9.81. So student A is accurate. Okay, so I hope you know the difference between accurate and inaccurate. So student A accurate, student B not accurate, student C not accurate, student D not accurate. So now let's look at precise. Precise is talking about the spread. So if we look at A, the spread is small. The difference between the smallest and the largest is only 0.05. The spread is small. If we look at B, the spread is large. The difference between the smallest and the largest is quite large. Oh, this one is 8.494, not 9.94. Okay, so let's jump to it. The answer is D. Okay, the answer is D. Why? Because they want precise. Is it precise? Yes, the spread is small. The smallest is 8.41, the largest is 8.50. So the spread is only 0.09. That's a small spread, but it is not accurate because the average of this value is way from 9.81. So ladies and gentlemen, the answer is D. Okay, so same for this kind of graphical example. Comment on the result with respect to accuracy and precision. Now, so we look at this. This is accurate because the mean is 9.81. Yeah, it's precise also because the spread is from 9.79 to 9.83. So it's just a small spread of 0.04. So small spread means it's precise. The mean is accurate means it's accurate. So this is precise and accurate. Okay. So if you look at this one, uh, the mean is 9.86, so it's not accurate, and the spread is large because it's from, if you look at this, is from maybe 9.81 to 9.991. So relatively, it's a large spread, so it is not precise, and the mean is not 9.1, so it's not accurate. Okay, so you can look at that for the next example as well. Large spread, so it is not precise, but the mean is 9.81, so it is accurate. So this one, the mean is 9.77, so it is not accurate. Okay, so it's not accurate, but it's precise because the spread is small. Okay, so you may ask, how much is large and small? It's normally a relative thing. Okay, it's a comparison thing. So this is where your judgment comes in. Now, this example 12, okay, this example 12 caused a bit of problem, uh, but it's a Cambridge question, so we have to address that. So, an object falls freely from rest and travel distance s in time t. A graph of t squared against s is plotted, and this is the graph that you get. Okay, so it falls freely, so we know this formula: s equals to ut plus half at squared. Okay, and they say it falls freely from rest, so u is 0, so the equation becomes s equals to half at squared. Okay, so they want to determine the acceleration due to free fall, so acceleration will be equals to, bring the equation one side, so it is 2s over t squared. Is it? uh, so yeah, 2s over t squared. So this Okay, but what I have is a t versus s graph. So let's not do it this way. It's a t square versus s graph. So let's rearrange this equation. I will have t square equals to 2 over a s. So the gradient will be equals to 2 over a. So if you look at this, the gradient is, okay, the question says that the gradient is 0.204. So 0.204 equals to 2 over a. Therefore, a is equals to 9.8039. So we know that acceleration due to free fall is 9.81. So this set of data give you an a of 9.8039. So we can say that it is accurate. Okay, we can say that it is accurate. So everything I mentioned here is mentioned here. Okay, it is accurate. But whether it is precise or not, it depends on how far the plots are onto the line. So you can see that there is a scatter. So in this case, uh, some of the plots are above, some of the plots are below, and they think Cambridge interpret this as there is a reasonable scatter. So it is not precise. Okay, so the official Cambridge answer that is given is it is not precise. It is accurate but not precise. Okay. Hmm. Hold on, let me move this. Yeah. So it is tempted. I think quite a few people would say that it is both. Quite a few people would think that it is accurate and precise. Okay, I think quite a few people think the answer is B, but Cambridge interpret this as not precise because there is a spread. So if all the points are on the line, then it will be both accurate and precise. Okay, because precision depends on spread. If there's a spread, then it's not precise. Okay, so that is this work example 12, which we have to go through with you. Okay, so we'll stop here for this first lecture. Uh, yeah, and then we'll continue from this point in the second lecture video. Thank you very much. Have a good day.